This presentation is called Time Out of Joint. It's a presentation about working with time and time zones in primarily in Java. For those of you who don't know me, I'm Addison Phillips. I'm a senior principal engineer at Amazon, and I happen to be the chair of the W3C Internationalization Working Group. And the title of this talk, of course, is initially taken from William Shakespeare, this quote that you see here, but really I'm borrowing it from somebody else who borrowed it. Was Philip K. Dick wrote a sci-fi novel called Time Out of Joint, and you could find it on Amazon. And what I found particularly interesting is that this particular copy purports to be written in Middle English with a publication date of January 1st of 1800, which I thought was apropos for a talk about how you can screw up date and time values. So this talk is an oldie but a goodie. I've given this talk before at Unicode some years ago, and then it went away in the attic, and I went on and did other things. And recently I had cause to come back and work with a number of developers at Amazon on date and time zone problems again. And once I started finding myself explaining how computer time works and how time zones work to people, it seemed like a good idea to resurrect the information and brush it up, and perhaps even bring it here where other people could benefit from it. Date and time values are really important in a lot of computer applications, and they form the basis of a lot of important things that we do at Amazon. It's super important to us because we make things like delivery promises, what time and what day you're going to get something, and or what a particular edition of something is, or that kind of thing. This is a screenshot from a bug from like a couple weeks ago, and it says, for the Dutch and Swedish sites, the release date showed as 9/24 as expected, but when we switched to English, for some reason the release date was 9/23, and it looked like this. Here are real screenshots of, on the left you have Swedish, and in the middle there you have the English, and you can clearly see that the release date is a day earlier if you speak English somehow. And the problem turned out to be, after we did some investigation, is that thing on the right side that none of you can read, which is somebody made a list of locales and associated a time zone with the locale. This is a crazy thing. Not only that, you can see I have sort of a dark colored rectangle. I blanked out a really long note, and it's introduced with important, in which the developer explained the crazy thinking that went into, if I'm showing ENGB, which happens to be the locale that we have for English on the Swedish site, then you should definitely have London time. No, that's probably a bad idea. When I originally wrote this presentation was some years ago when I worked on Kindle products, and one of the things we built was a feature called free time, which was a feature that allowed you to give a Kindle to your child and give them reading goals and give them awards, and for parents to track their children's reading behavior, how much time they spent, and that kind of thing. And so we had lots of messages like you see here, 5 minutes left until your reading goal, and here's an achievement screen showing, for a particular day what you did, summary for that day, and here's a list of achievements with a date on it. So dates and times are kind of mixed in through this whole application, and what happened was I saw lots of bugs like this. Free time is not awarding badges even though the user achieved the goal. You reached your goal message was delivered even though the person hadn't finished their goal. Lots of this kind of thing, and I was explaining to developers how date and times work in Java and the mistakes that they were making, and as I say, I was doing it a lot, and so ultimately I ended up making making a presentation and documentation out of it. The other thing that this talk is about is a working group note at W3C called Working with Time Zones. You can see the date on it is 5 July 2011. This thing has grown long in the tooth. Maybe my Christmas project this year will be to revise it. It's in need of revision, but there's some really cool material in here. Norbert Lindenberg, who you may see around the conference here somewhere, did work on use cases for time, working with time zones, and it's, I think, helpful to point out this document, even though it's a little bit crusty around the edges. And as I say, I hope to update it, but it's still valuable material, and this presentation is also much about the material that you find in there. So before we can talk about time and time zones in computers, we have to talk about how time works in the real world. And the source of time is something called observed time. If you think about before there were clocks, before there was Stonehenge, people set up timekeeping. They understood timekeeping based on the observation of events. So there's days, right? The sun is up in the sky sometimes, and sometimes it's dark outside. And there's a period of time that the moon goes through its phases. There's a period of time in which the stars in the sky come back to the same position in the sky. And people observed time based on these kinds of phenomena that they could see. And they set things like a year is how long it takes the stars to come back to the same position in some cultures. Or a month is how long it takes the moon to complete its cycle. And obviously a day is the light and dark period. And people notice things like there's a shorter, if you're away from the equator, there's a shortest day of the year and a longest day of the year, this kind of thing. These are observed time values. Computers don't use observed time values because they can't see, generally. So they use something that we call incremental time. Incremental time is the number of clock ticks since an arbitrary moment in time, which we call an epoch date. So the Unix operating system, and many systems similar to Unix or based on Unix, Java is one example, use the Unix epoch, the milliseconds, sometimes nanoseconds, since midnight, January 1st, 1970 UTC. Why that date? It's completely arbitrary. So the problem we have is how we get between incremental time and what we call wall time. Wall time is the observable time, the kind of time that you and I all talk about if I tell you today is the 14th or that it's 5 o'clock. And you need two things. You need a calendar, which is a set of rules that describe all the different mechanics of the different units that we assign. This happens to be a picture of a lunar runic calendar from Estonia, not in modern use, but I thought it was attractive. The thing you can't read on the right side is the Wikipedia thing showing a whole bunch of different calendars in the world at large. So there's lots of different calendric systems for computing what's a month and how many days does a month have and how many, what year is it and that sort of thing. So you need a calendar that knows those rules because those rules are culturally based and therefore arbitrary, even if they're linked to observable phenomena. And the other thing you need is a time zone. We'll talk a little bit more about time zones. First, you have to know why time zones exist. In the observable time era, there was an event you could observe with a piece of technology like a sextant, which was local noon, what time it was when the sun was at the highest point it was going to reach in the sky. And the way people set time before they could travel very fast was everybody had local time. If you go to Europe and you see those beautiful churches with clocks on them, somebody set local noon on that clock, and then it would keep time on the mechanical clock, hopefully accurately, because you could set a local time. Well, what happened was, at some point, transportation got fast enough, railroads primarily, that local times became super inconvenient. Imagine printing, imagine you need to go meet the train at the station. And you need to know what time to be there, because if you don't get there in the window when the train is in the station, you'll miss it. Well, the train schedule was I leave at noon and go to the next town where I arrive at noon, because the local time there is noon. And the next town down the road, the guy's not very observant, and it's actually 1:30 or something. You don't have to travel very far, and the further from the equator you are, the less distance you have to travel west or east to change what local noon is, and therefore what the local time was. So this is super inconvenient in a world where you can travel fast enough to affect what time it is, and actually, have to print schedules and that kind of thing, and where you have somewhat light speed communication, like, say, a telegraph. So in 19th century America, we went from having 300 local times to about 100 railroad times, and then very quickly to standardization to more modern time zone-like things. In 1884, internationally, other parts of the world caught up with this as well, with the International Meridian Conference, which established Greenwich Mean Time. If you've ever heard of GMT, that's when it came from. And then in 1972, notice it's after the start of the Unix epoch, UTC was established and came into play. So what's the difference? GMT's day starts at noon because it's an observable time phenomenon, right? It's not, they were using the sextant to go out and shoot local noon in Greenwich, England, and that's when GMT starts. And AM and PM mean ante and post meridium, before and after noon in GMT, right? So, okay. The UTC day, by contrast, starts at midnight. You can't observe midnight. There's nothing you can look at that will tell you when it's local midnight, because the sun's on the other side of the earth at that moment, right? And there's also one other thing I'll briefly mention, UT1, the actual astronomical time, because the earth doesn't spin at a constant rate. And there's actually a service, the IERS, that keeps track of that. And if you've ever heard of leap seconds, this is where leap seconds come from. Unless you are working on, satellites or, rockets or things that require super precision, I'm going to ignore the existence of leap seconds. Most of our timekeeping systems pretty much ignore it. The clocks in your computers are not that accurate. So, a second here or there, they get fixed up by NTP eventually in most cases. So I'm going to ignore that. But if you do work in a super precision thing, hey, don't crash your rocket into the earth. Don't screw up our GPS from that. All right, so moving on a little bit, one of the things that you need to hear about is local time offset, also known as LTO. That's the difference between wall time and UTC in a given incremental time in a particular location. So at any specific moment in time, you will have an LTO from UTC. If you happen to be on UTC, that will be 0. If you are here right now, you've got about 7 hours difference right now from UTC because we're in daylight savings time. And a time zone is a region of the Earth that observes the same rules for mapping an incremental time to a given calendar's wall time. It includes the LTO, and this concept of daylight savings, in some parts of the world it's called summertime, and the transition rules for daylight savings, if there is any, and the amount of the change, the time of day of the change, the direction of the change that takes place. Daylight savings time, helpful to think of it as summertime because areas in the northern hemisphere observe it in the opposite time of the year from areas in the southern hemisphere because it's summer down there the other time of the year, right? Okay. It also includes historical variations. Time zones are under the control of governments. Governments do random stuff. They change time zones all the time. And so you need to know what happened historically. Time zone data is collected by IANA in the time zone database. This is a picture of the website. It's an old picture. They update often because they are under control of government. So 10 times in 2016, 9 times in 2018, 6 times in 2020. This screenshot was taken a few weeks ago, and we only had one change at that time. There have been 2 published changes to the time zone database since then, one of which is very highly controversial. Maybe if we have time at the end, we'll chat a little about what some of that controversy is. The time zone identifiers take a form that looks something like this: a continent or an ocean, / some exemplar city, or in some cases the name of an island or a name of a location. A very few time zones have 3 parts, like the America-Argentina Salta one you see at the bottom. These are much less common. There's only a few of them that are in modern usage. Again, region plus exemplar city. These identifiers have a lot of really great characteristics. For one thing, they're stable. They don't change. Occasionally, a city will change its name and will publish a new time zone ID, but generally the old one remains canonical. They're offset agnostic. America, Los Angeles doesn't say how far it is from UTC, does it? That's important because that can change, and it can change arbitrarily in funny ways. And they're unambiguous. Once you see this, it maps directly to a table entry in the time zone database, and you can find out exactly what it means, what the rules are that are associated with it. Okay, few more pieces of jargon before we really get into this. I mentioned incremental time, which is clocks ticking away inside the heart of every computing device, at least those that have battery back clocks and so on. A different kind of data structure for storing time is called field-based time. These are time values built out of calendar time fields: year, month, day, hour, minute, second, milliseconds, sometimes nanoseconds, plus an offset or a time zone in some cases. They're almost always directly convertible with incremental times. And in fact, a fully specified field-based time basically is a kind of incremental time. If you think about it, you can get the milliseconds or back out of it to get the incremental value. And they're usually proleptic. Proleptic is a $10 word, which means that they ignore historical differences going back into the past. So a proleptic Gregorian calendar ignores the fact that the Gregorian calendar didn't exist before sometime in the 1500s and wasn't adopted in many, many places around the world, some of them into the 20th century. It just says, we're going to use these rules for the Gregorian calendar forever, in all directions, which means, of course, that historical date values, like truly historical date values, can be wrong in a proleptic calendar. You can't represent them quite accurately in field-based or field-based time, and you may end up with the wrong values. There's one other time I need to talk about. Besides field-based and incremental, there's a kind of time called a floating time. That's a temporal data value disconnected from a specific timestamp moment in time. And by disconnected, don't mean like totally dissociated, but there's not an incremental time that completely represents that moment. And you may be having a hard time visualizing it, so let me give you some examples. The publication date of a newspaper or a magazine or a periodical is a floating time because it doesn't care what time zone you're in. It doesn't change its field values. It's a field, you can think of it as a field-based time. Your date of birth is a floating time value. Your birthday is the same day, regardless of where you are in the world. It doesn't start, when it's, it doesn't stop when it's midnight in London, unless you're in London. And so those are the kinds of values that are floating values. They're not connected to specific incremental times, but they refer to a clearly identifiable moment or a set of moments, and we can have we can do some useful things with that. So classically, back when I wrote this presentation, in Java timekeeping, there were 3 basic classes. There was a Java util date. There's also a Java SQL date. It's basically the same thing, which is an incremental time. It's the number of milliseconds since the epoch in UTC, period. At any given moment, it is the same time, Java util date time, everywhere on Earth, because it's in UTC. So if you go, system current time millis, it gives you the same value regardless of where your computer is running, and that's a Java util date. There's a class called Java util calendar. ICU also has a calendar class, which has the rules in it for computing wall time values from the incremental time and the date, using calendric rules, using a locale, and using a Java util time zone, which guess what a Java util time zone represents? Its IDs are IANA IDs and a few others, and it represents those rules for time zones. There are, of course, many calendars. I'm going to flip over here for a second. So here's a little demo program we have running on our internal I18N site at Amazon. And what's interesting here is that it lists the different calendars that are available in ICU. So who's got a favorite calendar? I don't know if anybody can read this. How about a Buddhist calendar? And I can click submit, and you can probably see that the year changes. And I can pick, the Buddhist calendar isn't that exciting. Let's pick the Hebrew calendar here, and now we see that the month and the year both change, and the day number changes. You see that? Same time value being formatted in different calendars. So the rules inside the calendar go, okay, I'm going to take these milliseconds, and I'm going to break them up into hours, minutes, and seconds, years, months, and days, according to the rules of this particular calendaric system. Let's see. All right. About the time I made this presentation, there was something else going on. There was those classes were not very helpful to developers. They're hard to work with. They're the source of all of the bugs that I had, because the only game in town is an incremental time, and you had to do special things to keep them from doing unexpected stuff. Like if you had a floating date value, you had to do a lot of work to keep the numbers in the date the same, regardless of where someone was looking at it. And it was really hard to build a date, because you had to make this heavyweight calendar object and so on. And so somebody created a library called Joda, which was eventually, a version of it was merged into the JDK as the temporal classes. If you've been around the conference, you've heard people talking about adding temporal to JavaScript. It's the same general collection of ideas, much easier to work with classes which work in terms of calendric fields, field-based times. And so here's some pictures of the classes from the Java.doc site. So durations, an instant is an incremental time. Local date, time, and time are floating time values. So there's a set of classes, temporal classes, for floating time values. And those time values will stick to the numbers that you give them regardless of time zone. So that makes it much easier to work with floating time values. The month, day, offset date time, et cetera, lots of those. There's also a chronology package, and those are the different calendars. And so Joda time provides for different calendars. And the temporal interfaces provide you different ways to extract values and query values from a time value. You can find out what month it is, or what the difference is between two times, that kind of thing. And then there's some stuff we're working with time zones. One other thing to bring in here is serialization forms. The most common serialization form for date and time values, one I recommend that you think about if you're going to build a wire format, is ISO 8601. ISO 8601 is cool, but ISO 8601 has a bazillion options for different ways to serialize date and time values. And depending on what you're doing, you might need to choose a different serialization. The number one thing I can recommend to you is do not invent your own serialization scheme. Don't use simple date format to make your own little picture string that you're going to use to exchange dates with people or times with people. Use this standard or something that is derived from this standard. RFC 3339 has got several that are common on the internet, for example. Here's an enumeration of different ISO 8601 types with their friends from java.time classes, what they parse into successfully if you use the date-time formatter to parse the 8601 value. All right. Finally, I can talk about the working with time zones document. We'll start with one more concept, which is the timeline. The timeline is, imagine a line, and there's a point on it, which is the epoch. The epoch is when the time value, the incremental time value, is 0. Negative numbers are before 0. Positive numbers are after 0. They just mean there are times before or after that arbitrary point. In some parts of, for example, Joda time and java.time, the timeline can be arbitrary. You can make it whatever you want. But the most common timeline to use is the so-called ISO timeline, which is a proleptic Gregorian calendar with the Unix epoch. So 0 is midnight, January 1st, 1970 UTC. That's the most common timeline that you'll find. So the most common kind of time value is a time stamp, which is just an incremental time, basically, the number of clock ticks since the epoch. And the great thing about those is that, like I mentioned earlier, at any given moment, it's the same incremental time everywhere on Earth. So you can take timestamps collected from myriad systems all over the place and just merge them together. And they will naturally order themselves into a sequence of events, because they're all based on the same timeline with the same reference point, assuming your clocks are set correctly in your computers and that sort of thing, right? So it's really easy to work with incremental time values when the only thing you care about is whether something happened before or after something else when you have timestamps. Now, some systems have only past events, and they have something that they care about in the past event as to the wall time that it was when the event occurred. And a timestamp can't tell you that. A timestamp can tell you what time it was everywhere on Earth in incremental time, but it can't tell you what the local time was. So you need one more piece of information, which is the LTO, the GMT offset that you sometimes see in timestamps. Past events have a fixed relationship with UTC. Whatever the LTO was, that will be the LTO of that time value forever. And so you don't need a full time zone in order to find out what time it was. You just need the offset. So if you only care about past events, you're okay to just store an offset value. What about past and future events? What about future events? If I tell you the offset of something is GMT minus 7, what does that mean about the wall time of that? What if the rules change? Or what if there's a daylight savings transition between now and whenever that future event is? What happens if the government decides we're not going to observe daylight savings time anymore? Or we're going to double daylight savings time? So you need a way to be able to fix all of the future time values should that occur. And so you're going to need, the easiest way to do that is to have a time zone identifier, because then you just fix your time zone database and it fixes the time value that you have stored. Mind you, if you use the time zone and the time to do something like schedule an event in a computer using an incremental time, you need to find all those incremental times and perform whatever adjustment when you fix your time zone database, right? You can also have recurring events that recur, like a meeting that happens every week or a process that happens regularly, bearing in mind that a week is not always the same amount of incremental time, right? Daylight savings time transitions can happen for various people participating in the event, and so the week could have more or fewer hours in it for some people, depending on what their time zone is and what they're experiencing. Recurrence rules can be frighteningly complex because they have all of these different fields that you might need to collect. This is a picture from Outlook. It's one of the most scary pictures. This is like a dialog box in need of internationalization. Even though this, I'm sure I could switch languages and it'll show up and be fine. Here's a different tab of the same thing. Recur every 1 year on the second Thursday of October. I wonder how often that feature is used. Okay, there's the other kind of recurring time that can appear in systems which are shorter period recurrences. And the thing you want to think about there is it wall time that I care about, or is it monotonic incremental time that I care about? So if you have a cron job and you want it to run every hour, you just increment the clock by, the last run time by an hour's worth of time. 60 times 60 times, you know how that works, right? If you want it to run at a specific time of day, though, that's where you can get into trouble. Imagine that you set up your system backup to kick off at 1:30 in the morning. That's a good time. Nobody's using the system then. There's a day of the year where 1:30 in the morning doesn't occur because daylight savings transition jumps over it, right? And there's a day of the year where it occurs twice in some time zones. So you have to think about that and be careful that you insulate yourself from having bad things happen. I didn't get a backup, and I got a backup, and then the backup started again, and that caused, a contention problem, and bad things happened. And then you have floating time values. And I mentioned those before. You have to identify that these are different from your regular time values because you have to handle them differently. If you don't, you get into this kind of problem. This is, on the left, you see some floating time values, and then I've associated an offset. Z is UTC. The top one is -7 hours, which is currently America, Los Angeles, right? And you can see the incremental time values that those hexadecimal numbers, which aren't very helpful and human readable, those are different. So if you just take your floating time value and you shove it into a Java util date and then you print it out, you may get a different value than you expect. We can show you that. So here is, on the top, here is a timestamp. On the bottom is the same timestamp after we've interpreted it through a Java util date and a time zone. At the moment, these values are the same because the time zone is UTC. But if I use my handy dandy time zone picker and I find Pacific Daylight Time, notice that the 12th is now the 11th at some hour, right? This would be bad if you're Jeff Bezos and you're vacationing in the Galapagos and you can't figure out why the New York Times is always yesterday's edition. Maybe that's why he bought a newspaper. I don't know, but because we really did get that bug back in the day. And that was because of that exact problem. The publication date went into a Java util date and came out with the time zone on it. Oops. Okay, I'm so glad I switched away from that. So here's a little demo to help you visualize some of those things. What you see down here in the bottom, I hope you can read this, there's a variety of different outputs for what are basically, I put some fields up here in the top. And right now, this is set to 1970. 1 is January, 1 is the first day of January, midnight, and you can see that the incremental time is 0. let's add 1 minute. And now it's 1,000. It's 1,000 milliseconds later in incremental time. So, you know, set that back to 0. Let's make this 2021, 10, 14. Okay. So we have a Java time, some enormous number of milliseconds. The local date value is what we expect it to be. The local time is midnight. Let's, just for giggles, let's make it 1 o'clock in the afternoon. Okay. The instant, this is an incremental time in temporal, is what you expect it to be, sort of, 1300 UTC, because the time zone's UTC. The zoned date time says the 14th at 1 p.m. UTC. Here's our friend the incremental Java util date. Notice that it's 6 a.m. Pacific Daylight Time because we're 7 hours behind, right? So a different time value coming out of that incremental value. Now, this presentation partly was resurrected because I was working with a developer. We have our own message formatter at Amazon, and one of the things message format does not support is temporal types. And so we went into our message formatter and we wrote support for temporal types. And we had the question what to do when you're handed a temporal type and the temporal type doesn't have all the pieces in it. So a local date is a floating time value. So the fields in it don't want to change based on the time zone. So you'll notice that the local date here, I'm sorry I didn't make this selectable, is October 14th, 2021, because that's what the fields say. And you'll notice that I'm showing you the time portion. There is no time portion in a local date. If you try to query it, you'll get an error. But we carefully stage manage that because, of course, underneath the hood, date format needs a date object, an incremental time, and so we adjust it all so it's midnight when there's no time portion. Similarly, a local time has no date portion, and so if you try to access those from a temporal, you'll get an error. So we carefully stage manage that to be January 1st, 1970. That's kind of an arbitrary choice, but at least it makes some kind of sense. And the incremental value that comes out of it is the number of milliseconds represented by the local time. Finally, we have an incremental value with a time zone and a floating with a time zone. And the reason that's interesting is because I can change the time zone in my formatter. Yeah, okay. We'll pick El Salvador. Okay. And so now you can see that the incremental values are oops, did I do that upside down? I did it upside down. So I can change this one here. Merida, whatever that is. Okay. When you move things through multiple time zones, you can get very different values out of things than you expect. Notice that the floating time value on the bottom line is still a floating time value. It's still 1 p.m., regardless of how many time zones I put it through. But the incremental time value is moving around based on which time zones I'm choosing. So Australia, Curry, update. Oh, incremental time, October 15th at 5 a.m., floating time, still October 14th at 1 p.m., right? Which is what I want, even though the time zone is different on the formatter. Does that make sense? Kind of clear? Approximately understandable? Okay, so step one in your life is identifying which things are floating times and which aren't. If you make a value a floating time that isn't a floating time, its numbers will stick to that value, and that's not really what you want from, like, say, a timestamp, right? Then you need to decide what data you're going to need in your data structure. you're going to start with a timestamp value of some sort, either a field-based timestamp or an incremental time, depending on what is most convenient for you. And then you're either going to need an LTO or a time zone when you're working with anything besides just a pure timestamp value. I generally tend to recommend people store a real time zone and work with real time zones, but if you're only working with past events and you understand your case, you might just store the offset. And then if you have recurrence, then you need to structure data for your recurrence rule and store what that's going to be. So let's look at different things. So timestamps are straightforward. You collect the system time and you log it away somewhere. So if Rover is reading on his Kindle, he started reading at some time and he stopped reading at some time. The offset that you see in the timestamp isn't very interesting for the timestamp purpose, but it lets us calculate the incremental time. But those are also past events. So one of the things that can happen is that we might need to have the most recent page read shown to the customer. And so when it says, you were reading this today at 12:18 a.m., that's wall time. And so I need to know your offset, at least your offset, because it's a past event, in order to compute that it was today at 12:18 a.m. and not just an incremental time that has no connection to a specific wall time. If you have past and future events, then you need to think about how you're going to compute things and what the relationship is. You're going to need a time zone, not just an offset, because funny things happen. So the date that's here, November 6th, is a special date because that's the date that we switched in that particular year to back to standard time in America, Los Angeles. And so, America, Los Angeles is an interesting timestamp value. If you're doing recurring events, you'll need to think about the recurrence rule, as I mentioned before. Floating dates, we've talked about how those go. Remember that no matter where the user goes, you want the date to stay the same. So identifying floating dates can be a little tricky sometimes. Here's an achievement that a customer had that we show to people. Setting the time zone on the device shouldn't cause the date to change. That's a floating date value. And it can be a little tricky for developers to recognize that it's not just an incremental time and I'll get a date formatter and I'm good, right? No, you need to do something to make sure that you're using a floating time value. If you're using Java util date and not using temporal, the thing I recommend is to use UTC religiously for all of your floating time values. Zero out the difference, do adjustments as you need to. How are we doing on time? Good, okay. But modern Java has floating date and time values in it, so use those if they're available to you. You might need to use incremental times to compute values that belong to a floating time value. So here I'm showing a day's activity, and what you have are a bunch of timestamp values, hopefully with at least with LTOs, that you need to use to accumulate information and data that belongs to a floating time value, knowing that, for example, sometimes the customer travels, knowing that sometimes your kids will cheat and change the time on their device to try to rack up the points, right? So you want to be guarded against those things. Skip over that. That means that when you're processing values, you need to think about how those values slot into a floating time bucket, if you will. And so if you're trying to say what a day is, it's not always 86,400 seconds. I'm gonna kind of skip over this. One of the cool things that, again, Joda.time gives you is the ability to just compute directly variations in time. Incremental times, you subtract two incremental times and you get a number. It's kind of hard to use that number to do very much because it doesn't It doesn't tell you what its fields are. You can shove it in a calendar and kind of query it, but that's not super convenient. Whereas duration is an interface in temporal that you can use to find out the difference between two time values in terms of fields. All right, last piece, picking time zones. Super commonly, when people build a new system, they want to build a time zone picker that's better than the ones that came before. I don't blame them. Time zone picking sucks. And often they will have a map. And the first problem that you face is that there are not 24 time zones in the world, even though there are 24 hours in a day. In Java and the IANA time zone database, there are over 600. How many of those are really useful time zones? Well, the answer is not 620. My current answer varies depending on how the time zone database is mutated most recently. This slide says 281, but I haven't actually looked in a long while. And the problem is that 620 is too many. Here's the simplest time zone picker ever. It's a list of all of them, and you can see the red arrow is pointing to the scroll bar thumb. You probably can't see it, but it's this big because there's 620. And of course, nobody knows what their IANA time zone database name is. But here's a little program, and it's got a checkbox, show display names. Here's the IANA time zone database with the display names of times. And there's a lot of Pacific time. US Pacific, System 5, PST 8 PDT, Mexico Baja Norte, Canada Yukon, right? And so forth. New Zealand's got a bunch. There's a ton of mountain times. Mexico Pacific time, right? A whole lot of different time zones with actually different rules that have the same display name. And yeah, I can turn it off, and now I have the other thing, and this isn't very helpful either, right? So okay, not that. I did that. Okay, so an interesting insight is that there are only 23 countries that have more than one time zone. So if you know what country someone's in, you can figure out their time zone from their country straightforwardly. So that's kind of helpful. Several of them only have extraterritorial holdings, mostly islands. Like Ecuador owns the Galapagos Island. Their second time zone is the Galapagos Islands. Spain's a special case. Portugal has, what is it, the Azores or something, and so those are the extra time zones there. So, but all of these have additional time zones. So you could narrow down the list and only have a complex thing for people if you can't figure out where they are that way. All right, another problem with maps is that there's border disputes. And the red countries are countries that are currently have border disputes going. I don't think the one between Canada and Denmark is too exciting and will affect your time zone picker. But maps actually look different depending on who's looking at them. And if you think about it, maps are kind of futzy because, you know what? Governments change the rules for time zones all the time. And so you don't just need to change the shape of the map because of where the governments have drawn their borders, but also when the time zone rules change, you need to change the borders in your map. And that's a pain in the ass. So don't do that. So not a map. You use GeoIP to help you, but your IP address isn't always helpful. If you are a 3G, 4G cellular device, you can look at the tower, if you can see a tower, and that could be helpful. But at some point, you're going to need a user interface for this. So what are you going to do? So a few years ago, some years ago, I worked with a developer, Linus Tanaka. He's no longer with us, I'm afraid. And by not with us, I mean he's passed away. Yeah, but he did the work for our internal library for time zone util and time zone grouping. This is similar to some work in ICU. They have meta zones and all this stuff for managing time zones. But what we did was we took all the zones and we picked our own epoch date, 2009, and said all the time zones that have the same rules since 2009 get to share a time zone. to simplify our list. So that's how we got from 620 down at that time to 281. And to show you what I mean, I'm going to pull up our demo program. What we did was we divided up the Earth into regions, and because it was us, we got to pick the regions. You might have noticed that the time zones for the Americas were all America, so Argentina is in America in terms of time zone IDs. Well, customers didn't find that having every country in the Western Hemisphere in a single block of time zones was very approachable, so we divided North and South America. And then because, sadly, we sell a lot of things in the United States, we made United States special, because Americans are not really good with lists. So I can pick North America, and here are the time zones that we have that are unique in North America. It's more than you might think. So let's go United States to make this a little easier. Eastern, Central, Mountain Time, Phoenix, because the rules are different. Pacific Time, that's LA. Alaska Daylight, Hawaiian Aleutian Time, no daylight savings. And those are the different time zones. Let me click on one. Let's pick New York. Here's a list of all the time zone IDs that we lumped into New York because they don't have different rules since 2009. Detroit, Fort Wayne, all the Indianas, Kentucky's, Louisville, Montreal, New York, et cetera, a whole bunch that we lump into that time zone. I can go somewhere else, like let's say Europe, let's say Paris, and I have an impressive list of time zones that share rules. Now, I mentioned the controversy at IANA earlier. That's the controversy, is the maintainer decided to do a similar exercise and did away with a bunch of time zones, put them into what's called the backlist of time zones. Not realizing that a lot of us depend on this, or that, hey, one of these governments, tomorrow the government in San Marino could wake up and change their rules, right? And then we'd be in trouble because there's no actual zone to represent that. So this is the underlying code, and it made its way into devices, and so you could see that we made user interfaces for customers to use. If you own a Fire tablet, you've used this interface perhaps. So, questions? Did I confuse the heck out of everyone? Sir? Yeah, the question is how to prevent yourself from getting out of date with the time zone database because it changes regularly. What happens in the case of ICU is as soon as a change has happened, the ICU folks prepare the change and commit it to the ICU repo. In addition, there's a time zone updater utility you can use to patch your distributions. Without having to go and rebuild the entire universe. So it's a super common problem. It's a terrible problem because you have to update all of your code in the field in sometimes almost real time. The most recent change to the time zone database is Samoa's decided not to observe daylight savings time because of COVID. And they've given like weeks to respond to that. And that has to go through the time zone database, through every computing system, not just ICU, but think, your operating systems all have time zone data in them. Your JVM has time zone data and so on. They all have to get patched. And the main thing is, establish a process and track it. My team does that for Amazon, and it's as soon as that email comes up, there's a developer, we actually track it. There's a ticket cut immediately, and and our system pulls the data and is building the thing, the moment it comes out and running the test sets, and then we get to go chase 46,000 developers and consumer to fix their systems. So, Rich, you had a question?
Yeah, actually, I have two unrelated questions. Hopefully they're not too stupid. One, you talked about all of the code stuff was very Java-centric.
Yeah.
I think I know the answer to this, but is there anything analogous to the java.time stuff in ICU or any other facility for handling floating dates?
There is. The question is there anything in ICU for handling for this? There's some. The little demo I showed of our website that's ICU's calendar classes in action, and but ICU doesn't recognize a floating value. It doesn't have It doesn't recognize java.time types generally. I think the the date formatter class does. But I'm not perfectly certain of that because I know I've been patching things, using our own code. But I know that there's some thought there. And then other programming languages are going through this. JavaScript obviously is adopting these things and using ICU-based data to back what they do in the temporal thing. And second question? It depends. The question is whether it's harder to convert a floating date between calendar systems. It kind of is, because the challenge that you get into is that two things don't match up, right? Unless the other calendar system is like Gregorian based in some way. It's just like the year number differing. Then you can kind of just slop it over. But most of the time, what you need to do is use a time zone and an incremental time, because it's hard to say what those are. Now, I think some of the temporal classes know the difference and can do that, but I haven't tried it personally. It's not too common to need to do the other calendars in the stuff that I'm doing, but so it may be possible. Yeah, I mean, and the quick and dirty way, of course, is just, incrementalize it and control the time zone that you're using. But, yeah. So, cool. Other questions? Cool. How are we doing on time? We have 2 minutes before I think they have the... Oh, go ahead. I'm sorry, I couldn't quite hear. IANA is the Internet Assigned Numbers Authority, so they maintain many, many registries for Internet-related stuff. And they happen to have taken over maintaining the time zone database. So if you go to iana.org, I think it is, you'll see that one of the links there is the time zone database stuff. So that's the site to go to get at the files that describe time zones and so forth. It's called tzinfo. Is the name of the file that they produce, one of the files that they produce, and it's a voluminous, somewhat machine readable thing full of commentary. It's a fascinating read. For most of us, though, we get our time zone data from our systems in different ways. And so, for example, if you're an ICU user, you can look at Java util time or COM IBM ICU util time zone. And all the things related to that in ICU, or java.time zone ID or java.time util time zone. Hopefully that helped. Sir?
How do you guys rate, like Amazon?
I'm sorry?
How do you guys into the time zone database? What date
Um,
You guys use ICU or?
we use ICU. ICU is the core of our own internationalization stuff in different frameworks, and so we patch our ICU and do distribution to people using our internal distribution, software distribution tools. There are other teams that are affected, like the JDK team, JVM team, like the Corretto folks. They process the same thing and distribute their patches as well. So, and I don't know about like the Linux people, but I'm sure they're doing the same thing. So lots of teams actually are responding to this. And then obviously, if you're not Amazon and you're dependent on somebody's frameworks and so on, you have to get those patches and install them, or you'll wake up one morning and your computer's making bad delivery promises in Brazil or something like that. So, cool. Any other questions? I think the next event is refreshments. I will be here if you have questions that you're scared to ask in a public forum, or you just want to chat about things. Feel free to come up to me individually. I love talking to all of you. Thank you for coming to my talk.